terms of graphing systems of linear differential equations, when we talk about graphing the phase plane, when we get into linear systems, our starting point is always going to be to sketch the nullclines, to find the equilibria, and then to move forward with our analysis. If we know that we have a linear system, so our only equilibrium is 0, 0, we can definitely start by sketching the nullclines. But if we know what the eigenvectors are, that actually gives us a different piece of information to get started on the graph. So there's kind of two different places that we can get started. So I'm going to go ahead and get my, my eigenlines in here. So -1, 2 says 1 to the left, up 2. So 1 to the left, up 2. So this line is going to do something like that. And this other line, 3 to the right, up 1. 2, 3 to the right, up 1. Something like that. So I know that actually along these eigenlines, I know exactly what's going to happen. Because if I start along either of those eigenlines, I know that my trajectories will stay on the eigenline, but shoot outward from our equilibrium. And I know they're moving outward because those lambdas are both positive. So if I think about starting somewhere not quite on one of those lines, which of those eigenvalues is going to influence my long-term behavior the most? So I'm going to argue that 5 is going to influence my long-term behavior the most. Because that lambda, if I think about my general solution for this equation, without finding the C1, C2, I know this is going to look like C1 e to the 2t times -1, 2 plus C2 e to the 5t times 3, 1. So as t approaches infinity, this one is getting pushed towards infinity much faster than this one because my eigenvalue is larger. So if I think about those two directions, I know that I'm going to get pushed outward in this direction. That's going to be my long-term, like, bigger push. So if I started here, I'm getting pushed out this way and pushed out this way. How do you have these curving? So I'm going to have. Right. So I'm going out this way. Is that what you mean by a U? Yeah. I agree. Because my long-term behavior is going to be dominated by my lambda of 5. So my long-term behavior, I'm going to get pushed sort of in this direction more strongly. So if I imagine my arrows as like pushing me around in the current, then I've got a little bit of push to the right, or sorry, I am currently standing at a weird angle. That's why I said right. So I've got a little bit of push in this direction, but I've got a lot of push in my purple direction here. Does that sort of make sense? So I've got a little bit of push in this direction, but a lot of push in that direction. And over here, I've got a little bit of push in this direction, but a lot of push in this direction. I will also remind you all that if we're not using RStudio or a calculator or some sort of lovely web app, Your picture doesn't have to be perfect, right? We're looking for sort of the general trend of the behavior. So I gave us a particular initial condition of x equals 2, y equals 2. And then I wanted us to sketch what do those graphs of x as a function of time and y as a function of time look like. So for starters, if my initial condition is that x of 0 is 2, then I know that I'm starting here at a value of 2. And if my initial condition of y of 0 was 2, then I'm starting here. Oh, I don't know why I labeled those backwards. Fun, 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 fun. My y is 2. And both of these, if I start at 2, 2, then I'm up here in the first quadrant. So I'm starting somewhere up here. So I know my trajectory is doing something like this. So both my x is increasing and my y is increasing. So in terms of the graphs down here, they're pretty boring. I know that my x is increasing and I know my y is increasing. The same thing, if I go to find my particular solution, I've got x is 2, y is 2. Because t is 0, when I plug that part in, e to the 0 is going to just be 1. So I'll have c1 times our first eigenvector plus c2 times our second eigenvector. Or if I write that as a system of equations, 2 is equal to negative c1 plus 3c2. And 2 is equal to 2c1 plus c2. Lots of options, but I was going to multiply the top equation by positive 2 and add them together. So 2 times 2, 4 plus 2, so I've got 6. My C1s would then cancel out, and I would have 6C2 plus 1 more C2, so 7C2. I get 6/7 for C2. And then it doesn't matter which one we plug it back into to get C1. I'm going to choose the top equation just because the coefficient on C1 is just a -1. So if I take the top equation and rearrange it, it says C1 is equal to 3C2 minus 2, or C1 is equal to 3 times 6, so 18/7 minus 2. And since 2 is 14/7, I think I'm going to get 4/7. 1, 1, 1 to the right, up 1. And this is with lambda equals -1. So directly along this eigenline, I know all of my arrows are decaying into 0. And along the line, that's 4 to the right, up 1. So 1, 2, 3, 4, up 1. So along this eigenline, since lambda is 2, all of my arrows are getting pushed out. So if I think about trajectories here, I'm going to start, if I start kind of close-ish to this vector, I'm going to get pushed in for a little bit, but I'm eventually going to spit out going that way. If I started somewhere over here, I kind of start going in and I get spit out this way. If I started over here, I come in and I get spit back out this way. If I start over here, kind of do something like that. Again, it doesn't have to be perfect, just kind of giving the overall impression of what's happening. So I give an initial condition of 3, 3. So 3, 3 happens to live on one of my eigenlines. So if I start right here, I'm just decaying in towards the origin. It was kind of a trick question. I mean, not really a trick question, but the fact that I'm starting on one of the eigenlines. Well, so my initial condition is that I'm at the vector 3, 3. So 3, 3 is on the line formed by the eigenvector 1, 1. It's not on the line formed by 4, 1, but it is on the line formed by 1, 1. So because that's my initial condition, I know I'm actually starting on the eigenline. And if I'm actually on that eigenline, then both my x of t and my y of t are decaying to 0. But let's pick another point. So I'm starting at 3, I'm starting at 3, and both of these over time are decaying into 0. Now, if we were to actually find the particular solution, that's also going to show us that these should both be decaying into 0. When my initial condition is on one of the two eigenlines, that means that my solution has no influence from the other lambda. That coefficient for the other lambda will end up being 0 when you go to work out the particular solution. Just for fun, let's sketch what the trajectory, or I'm going to pick this trajectory of mine, and I'm just going to call that A. And I want to sketch what the graph should look like if I'm on the initial condition of point A. So if I started at point A, my random point A here, I know that my x and y values are both starting positive, and because I didn't actually label it, I'm just going to pick kind of some arbitrary x and y values. And now let's think about what happens to our x over time. So as I'm moving along this trajectory, I started right here, and then my x value is getting smaller, 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 because I'm moving to the left. So if I think about this point in time, B, that's the smallest x value that I get to. And then x starts moving to the right again. So if I'm sketching the graph down here, my x gets smaller for a little while. And then it's getting bigger again. Now, if I think about what's happening for y at the same time, I'm gonna just subtly fix my curve here. And I'm gonna push myself a little bit like that. Okay. So if I'm thinking about what's going on with my y, I'm starting at some positive value here. My y goes down, but b is not actually the lowest y value. My lowest y value is somewhere down here. So I'm going to call that point C. So my y is decreasing to B, but then it's still decreasing a little bit longer to C. And then it's slowly increasing out here, but it's increasing really slowly. these nullclines and look at where dx dt is equal to 0, then if I solve this, I get 2x is equal to y. So rather than graphing, and let me do the other one here. So I've got dy dt. If I set that equal to 0, and I've got x minus 2y. So that means 2y is equal to x, or y is equal to 1/2 x. So what's special along my nullclines, so not the eigenlines, but what's special along my nullclines is that I know that one of these two pieces is exactly 0. So now I'm going to ask the hard question. If my x is not changing, then what direction will my direction vector point? Left, right, or up, down?
If my x isn't changing.
Correct. Will I point up, down, or left, right?
If my x doesn't change, it will go up, down,
Yep.
or right, left, up, down.
So this is going to go up, straight up and down along this nullcline. Y is not 0. Dx dt is 0. Let me take a step back. Okay. So let me go back to just our equations for a second here. If I asked us to find some direction vectors, like to sketch out some direction vectors, pick a point, any point. 2, 1. Okay. So if I were thinking about sketching a direction field and I'm standing at the point 2, 1, and I wanted to know what direction the vector pointed there, then I would get my change in x from doing -2 times 2 plus 1. So that's -3. And I would get my change in y, sorry, dy dt, not dy dy. And I would get my change in y from 2 minus 2 times 1, so -1.
0, isn't it?
Oh, yeah, 2 minus 2 is 0. Thank you. Thank you for that.
Changing y, changing x for where?
I'm standing at the point 2, 1. And these differential equations, like if I were to read this out loud in words, this says the change in x I get from -2 times the x coordinate plus 1 times the y coordinate. Like that's how those direction fields get plotted, right? Is by thinking about this. So if I'm standing at the point 2, 1, then this says I should move 3 to the left, down, up 0, right? So this would go just, I'd have an arrow that pointed directly to the left. And if I picked another point, like, I don't know, 1, 3, I could also figure out what my direction vector should look like. So dx dt at 1, 3 would look like -2 times 1 plus 3. So that's a +1. And dy dt would look like 1 minus 2 times 3, so -5. So if I was standing at the point 1, 3, my arrow should point 1 to the right, down 5. So something like this. And we could sit here and plot a whole bunch of these little arrows, right? And that's how we would build a direction field. I don't want to draw the direction field for this because it's going to get messy in a hurry. But I do want to come back to the magic of nullclines. So in that same sense, if I had to find a direction field along my dx dt nullcline, I know that the x component of my direction vector is going to be 0. So I'm not going to have any left or right. I might have an up down, but I'm not going to have a left right. Anywhere along my dy dt nullcline, the y component of my direction vector will be 0. So the only directions I could point are left, right. So what that helps me do on a phase plane down here is, so if I sketch this nullcline, y equals 2x. Okay, I missed the origin, but pretend that I drew that perfectly through the origin. So that's y equals 2x, and that is my dx dt is equal to 0 nullcline. And along my dy dt is equal to 0, y equals 1/2 x. So y equals 1/2 x, and that is my dy dt equals 0 nullcline. So we happen to have already chosen a point 2, 1 that lives on this nullcline right here. So I'm going to borrow that 2, 1 point. And just because it went off the screen, I'm going to replicate my differential equations down here. dy dt equals x minus 2y. So along this nullcline, when we were standing at the point 2, 1, we plugged everything in, and at 2, 1, we found that our vector pointed directly to the right. And everywhere over here along this nullcline, these vectors, I said right, and I pointed to the left. I meant the left. Because when we plugged in the point 2, 1, we got that our value for dx dt was -3 by plugging a 2 and a 1. So along there, all of those point to the left. So let's pick a point along this nullcline, like 1, 2. If I'm at 1, 2, I already know that I live on this line. So my change in the x direction should be 0. My change in the y direction at the point 1, 2 would look like 1 minus 2 times 2, or -3. So I'm going to be pointed straight down. There's a reason that I only drew this that I only drew my arrows in the first quadrant. And now I'm going to ask us something. I'm going to revise, let's bring something back from 19A.
Why 1 to push down? You plug 1 to dy dt or dx dt?
Well, when I plug it into dx dt, what do we get?
0.
Right, so that's how I know it doesn't move left or right. Because I'm already on a nullcline, so I'm already on a place where dx dt is 0. So I have to plug it into dy dt to figure out if it goes up or down.
And then 2, 1, you plug it in dx dt.
Correct, because I already knew the dy dt was 0. Yeah. Okay, so now 19A thing. The only way I can change from positive to negative is if I go through the magic number. Yes. So the only way that the sign of my derivative can change from positive to negative is if I passed through 0. which means if I'm moving along this nullcline, the only way my sign can change is if I pass another nullcline, if I pass another place where the value is 0. So I'm going to do a test point down here. Still has to be on this line. So my test point down here, how about -2, -4? That should still be on this line. Because it's on this nullcline, what's my dx dt equal to? Right? So I only have to check the dy dt equation. So -2, I'll write it. -2 minus 2 times -4. So it's positive, which means my arrow points up. So we passed through this a nullcline where dy dt was equal to 0. So in the y direction, I flipped from being negative to being positive. It is looking like it could be stable because my arrows are appearing to point in towards the origin, right? And if I pick a point out here, has to be on this line. So let's say that's the point -4, -2. Since it's on this eigenline, I know dx dt, sorry, I know dy dt is 0, so I just have to check the dx dt. So at -4, 2, I would have -2 times -4 plus -2, which means I'm going to point to the right. So there are two options for how we think about our phase planes. We can either frame all of the graphing around the nullclines, or we can frame the graphing based on the eigenvectors, which essentially tells us what's happening kind of between the nullclines. And when we move into nonlinear systems, we're going to have to be able to put all of that together on one graph. So this is sort of preview of coming attractions. Part of the reason that I brought it up is this is actually shown in section 10.2 of the textbook. So I know you haven't done the nullcline stuff in lecture, but again, I'm just sort of making guesses of what that next homework assignment might be. And this is definitely a tool that we need when we move into the nonlinear. We definitely have to be able to graph along nullclines. So let's go check if our guess was right. Let's see if this is stable. So go ahead and find the eigenvalues to check if it's stable.